general, you have to think probabilistically with probabilities and statistics. And, that's the nature of quantum mechanics. Okay, so the probability that this one gets this result, when you measure it, you obtain this result, and hence this superposed wave function collapses, just changes to this one. The probability that happens is equal to the square of this number here. So you can look at this Ci as a form of the component of this wave function in the direction of this wave function. Looking on this as a vector. So this might be a general vector, and you can look on this vector here as one of a basis set. I'll be coming on to that a bit later. If you're not familiar with what a basis is, go back to earlier sessions. If you're thinking in ordinary three-dimensional space, and you have a general vector v, v wiggle, and you can express that vector v in terms of a component length c1 along the x-axis times the unit vector ei. Well, it's in a previous session. Plus, well, I'll just use x, y, z. So a general vector is just x ei plus y ej plus z ek. And that ei, ej, and ek, they are three unit vectors. And they're vectors, so the direction is important. So ei is the unit vector along the x-axis, positive direction. The y is the unit vector along the y-axis, positive direction. And the what do I call it? ek is the unit vector along the z direction, positive direction. And those three unit vectors, ei, ej, and ek, together as a set of these three unit vectors, they are called a basis because they serve as the basis, as the foundations, if you like, from which you can construct any three-dimensional vector, v. Right? So, in a sense, these wave functions here become the set of them, all possible wave functions you can have. So if you have big N possible measured values here, where this I ranges from 1 to n, let's say, big N, then you'll have big N different wave functions here. So your basis will be these vectors and n of them. So this wave function here is a general wave function in an big N dimensional space, right? Thinking now of wave functions as vectors. And so this wave function here now is a general vector in an n, big N, dimensional space, where these wave functions here now serve as the basis vectors. Okay? So you're thinking vector spaces and quantum mechanics. So the two just merge after a while. You just think in those terms. All right. So that's the general concept. Now let's apply these ideas to energy. So now the observable is A here is now the energy. So E instead of A we took E, capital E, and the psi these now. They correspond to the eigenstates of the energy in the Schrödinger equation. Okay, so let's assume now that these psi i's are stationary energy levels. Now, remember what stationary means? That means when the potential in the Schrödinger equation, the V, is not a function of time. It does not depend on time. Okay? So under those circumstances, you can solve your Schrödinger equation and you get solutions for the wave function well, they're these. Okay. Now the question is, this kind of thinking, which we showed earlier was true for position when the observable is position. Question: is it true when your observable is energy? Right? E is that? So we can, for this in the next session or so, we'll show. Well, the next 3 sessions, in fact, at least, will show that that it is true that this kind of thinking here carries over for when the observable is energy, and later we will show it's true for angular momentum, and so on and so on, until we sort of generalizing. We're using induction, if you like. It's true for this case, and it's true for that case, and it's true for this case. And then you begin to think, oh, well, it's probably true in general. Okay, therefore it's a basic principle, basic rule, if you like, a fundamental rule, right, or a formal rule of quantum mechanics. So very important. All right. So so the question mark here. So if these wave functions here now are the wave functions that correspond to discrete energy levels from the STI, the Schrödinger time-independent equation, okay, are they orthogonal? Or expressed in other terms, is the bracket, is it equal to 0 if these two states are different? Right? If they correspond to two energy levels that are different, EM and EN, corresponding to these two wave functions. Right? So bracket, remember you can, bracket's just a shorthand notation, if you like, for the overlap integral. So if psi m and psi n are two wave functions corresponding to two different discrete energy levels from your Schrödinger equation, are they orthogonal? That's the question. So we will now prove that they are. Yeah, surprise, surprise. Okay. So we'll now prove that this bracket, this I haven't bothered writing in these terms, but this bracket is just this. We'll prove that this is 0, where these two wave functions correspond to different energy levels, discrete allowed energy levels for a STI, a Schrödinger time-independent equation, right? So now let's do a fairly concrete example. So we'll keep it fairly simple. So we'll use the one-dimensional case, the 1D case, and we have our Schrödinger equation. And let's say we have two different solutions to it, corresponding to two different energy levels, because we're talking energy now. Our observable is energy, E. Okay. So let's say these are two different solutions, two wave functions, corresponding to the. So this is this, right, and that is that. Just going back to our old terminology. So we have two wave functions, UM and UN, and their corresponding energies, allowed energies. They're in fact eigen energies, they're eigenvalues, EM and EN. Let's assume they're different, right? Well, here's the Schrödinger equation. Okay. The general, the STI form, not the time-dependent form of the Schrödinger equation. We've hardly talked about that yet, but we will, believe me. But at the moment we're dealing with the STI, STIE, Schrödinger time-independent equation. Right, so here's the STI, here's one of them, and UN here is the second solution that we got. So UN, right? Now UM here is another solution to the Schrödinger equation by definition. So we can put, we can write down this as well. That will be true because this is a solution to this equation, this differential equation, this STI. But we've started, so if this n equals m, you'll have UN, and now conjugate everything. Just star the whole thing, the left and right hand side. Remember, to conjugate simply means change wherever there's an I, square root of minus 1. Wherever there is an I, make it minus I. Right? So you'll then get UM starred, UM starred, UM starred. Right? Now, so call that equation little a and call this equation little b. Now multiply a, this equation here, on the left by UM star. So you'll have a UM star d squared UN blah blah blah. Okay? And so call this equation b here, and multiply b, this equation, both sides, on the left by UN. Right? So now you have here, you'll have a UN d squared UM star blah blah blah. Right? Okay, take those two results, and then subtract them. And well, that's the end of the session, and we'll just continue on seamlessly with the next session. But you multiply on the left by both sides by this. You do similarly this equation by UN. You get the two results. You subtract those two results, and then integrate by parts. And eventually, you will end up proving that the bracket is 0. But I'm jumping ahead a bit. That proof will be part of the next session. Right? So what I'm trying to say is that these, in the case of when the observable is energy, when big A is E, then these two wave functions that are solutions to the Schrödinger equation with these allowed energies, they are orthogonal. So in other words, the bracket is 0, but we're yet to prove that, but we'll do that next session.